Hey everyone, it's Dr. Gray. I wanted to go ahead and work through questions number 3 and 4 of the 2018 Chem 1141 exam. So let's go ahead and begin. So question number 3 says, given the following reactions, H2O liquid, in the parentheses, goes to H2O gas, in parentheses, has a delta H of 44.01 kilojoules. The next reaction, 2H2 gas plus O2 gas yields 2H2O gas. Delta H is negative 483 kilojoules. The enthalpy for the decomposition of liquid water into gaseous hydrogen and oxygen, 2H2O liquid yields 2H2 gas plus O2 gas, is blank kilojoules. So this question is a Hess's law question. And essentially what this is asking us is, given these two half reactions, or partial reactions, we'll say part reaction A and B, given this information, what is the delta H for this final reaction? So the way that you approach this problem is what you need to do is be ready to flip either of these questions, or flip either of these reactions. So H2O liquid going to H2O gas has a delta H of positive 44.01 kilojoules. Now you can also look at this in the reverse sense. So if you wanted to take H2O gas and convert it to H2O liquid, then it would have a delta H of negative 44.01 kilojoules. So this is an example of being able to, or this Hess's law type of problem is one where you can flip a reaction and therefore flip the delta H. I always kind of think of the Missy Misdemeanor Elliott song, I can't remember, but you know, you flip it and reverse it here. Okay, so this is Hess's law. And the way that you're going to approach this is you're going to find the species that are similar. So in reaction A, we have H2O liquid going to H2O gas. Now, in our overall reaction, the one that we actually really care about a whole lot, we have H2O liquid going to 2H2 gas and O2 gas. Well, how could we contort these two reactions, A and B, in order to match up with this reaction below? And it's actually kind of simple. All that we're going to need to do is take this reaction B and rewrite it. And we're going to rewrite it with 2H2O gas goes to, or decomposes into, 2H2 gas plus O2 gas. Now the reason that you're able to do that, and the reason that we want to do that, is because we looked at the subscript, or we looked at the phases. So in reaction A, we have H2O liquid. We have H2O liquid on our overall reaction. Do we have H2O liquid anywhere else in either of these reactions? No, we do not. So this reaction A, we're not going to flip and reverse or do anything to that at this point in time. Reaction B, however, what we need to do is we need to get our reactants to be products, because our product in our overall reaction, those are 2H2 gas plus O2 gas. And our reactants in reaction B are 2H2 gas and O2 gas. So when we rewrite this equation, what we're going to do is rewrite the delta H. So delta H is equal to now 483.64. So it's not negative 483.64 kilojoules, it's positive. So once we've done that, I personally like to just go ahead and forget that this reaction ever existed. Okay, I can scribble it out because I'm not going to use that again. Okay, now a follow-up to that. Well, I've got my 2H2 for my overall reaction as products, and I've got O2 as a product. I've got 2H2 in my reaction B and O2 in my reaction B. The one thing that's a little bit of a problem is if you look at your reaction for reaction A, do we have a coefficient out in front of that? No, we don't. So what do we need to do? We need to multiply everything here by 2. Because when we do that, then we put the coefficient in front of our H2O liquid, as we see in our overall reaction. When we multiply this by 2, our overall reaction by 2, we also need to multiply the delta H by 2. And so I'm going to rewrite this newly formed reaction, which is 2H2O liquid decomposes to 2H2O gas. This has a delta H of 88.02 kilojoules. Now, when you look at this, what you're going to be doing is basically combining the reactants for both of these two reactions and the products in both of these two reactions. So if you wanted to write all of it out, you'd write out 2H2O liquid. So I will do that right here. Liquid plus 2H2O gas, because these are our reactants, and then these are going to combine to produce our products, 2H2O gas plus 2H2 gas plus O2 gas. Now, what is our delta H for this overall reaction? Our delta H is going to be the combination of 483.64 plus 88.02. And I'm going to plug that into my calculator real quick. 88.02 plus 483.64, and I come up with 571.66. So my delta H is 571.66, and that is in kilojoules. The last thing that I need to do, I've done this, but what I want is this reaction right here to match this reaction. So how do I do that? Well, I need to look at it, or take another look at it. What matches up and what doesn't? I see 2H2O liquid here, I see 2H2O liquid here. That's the only reactant. This is decomposition. Now the reaction that I've written out, I see 2H2O gas as a reactant, and I see 2H2O gas as a product. When I see 2H2O gas as both a reactant and a product, that means it basically didn't do anything, and so it's not really relevant to the overall reaction. And whenever I cross that out, because it's on both the reactants and the product side, what am I left with? I'm left with 2H2O liquid decomposes to 2H2 gas plus O2 gas. My delta H is 571.66, which brings me to answer option B. So your correct answer for this question is B. All right, I hope this is helpful. Now on to question number 4. Question number 4 reads, a 31.5 milliliter aliquot of H2SO4, that is sulfuric acid. This is a diprotic acid because it is H2SO4, so that would decompose into 2 hydrogen ions plus SO4, the sulfate ion with a 2- charge. The 31.5 milliliter aliquot of H2SO4 of unknown concentration was titrated with 0.0134 molar sodium hydroxide. It took 23.9 milliliters of the base to reach the endpoint of this titration. The concentration of the acid was blank. Okay, so this one is one in which we are going to want to use our number of milliliters of our base, the concentration of our base, and our base concentration, and figure out the number of moles of base. I like to do this sort of problem in this manner because I like to keep track of everything. So I'm going to write out my chemical reaction, H2SO4 plus NaOH. This is going to produce Na2SO4 because that sulfate ion is a 2-, the sodium ion is +1, so I've got to have 2 positive sodium ions in order to make an ionic compound, Na2SO4, plus my other product. Anytime I'm doing a neutralization or reaction with an acid and a base, I'm going to produce H2O. All right, so now I have to ask, is my reaction balanced? And I can tell you that it's not because I've got a diprotic acid and a base that's contributing 1 hydroxide ion. So what I want to do is just go ahead and put a 2 out in front of my sodium hydroxide. That balances my sodiums. I've got 2 sodiums on the product side. I've got 1 SO4 on my product side, and my reactant side I've got 2 hydrogens. So I'm going to count them all up. I've got 2 hydrogens, 2 more hydrogens. Okay, if I put a 2 coefficient in front of the H2O, now I've got the 4 hydrogens on my product side. So how many oxygens do I have? I've got 4 oxygens in my sulfate ion. I've got 2 oxygens in my hydroxide, so I have a total of 6 oxygens on my reactant side. I've got 4 and 6 because of that coefficient. I've got 6 oxygens there. So this was a quick and easy one to balance. And ultimately, this is valuable because it shows you that this is a 1 to 2 molar ratio. So for every 1 mole of H2SO4, you need 2 moles of sodium hydroxide to neutralize it. So, like I said, our earlier calculation was we need the volume of our base and the concentration of our base to figure out the number of moles of our base. So we have 0.0239 liters of our base. That is the same as 23.9 milliliters. Okay, so 0.0239 liters of our base, multiply that by 0.0134 molarity, moles per liter, and that's going to give me the number of moles of my base. My base, I have a total of, when I plug this in, 0.0239 times 0.0134. I am looking at 0.0003226 moles of sodium hydroxide. Okay, so think back a little bit. If we have 2 moles of sodium hydroxide, how many moles of H2SO4 were we able to neutralize? We were able to neutralize 1 because we have that 1 to 2 molar ratio. 1 mole of our acid, because it's a diprotic acid, requires 2 moles of sodium hydroxide. So we have this very small number, 0.0003226 moles of sodium hydroxide. I'm going to set up a dimensional analysis to figure out how many moles of H2SO4 that we neutralized. So one quick and easy way that you could do it is simply divide it by 2, but when we look at that in dimensional analysis, it looks like this, 32026 moles NaOH. We have 2 moles NaOH will neutralize 1 mole H2SO4. So there's our simple division by 2, divide that by 2, and we get, and I'm going to write this in scientific notation, 1.6013 times 10 to the minus, that would be 4 moles H2SO4. Okay, so that's how many moles of H2SO4 we needed. This question actually asks us, what is the concentration of our acid? And our concentration is evaluated in terms of molarity. So you need to know what that capital M is. That is moles per liter. Okay, if that's moles per liter, we have the number of moles of H2SO4. We need to divide that by the number of liters. Well, 1.6013 times 10 to the minus 4th moles divided by 0.0315 liters. So take that 0.00016013 divided by 0.0315, and you come up with 0.00508. So 0.00508. Ultimately, that means your answer is B. B is the correct answer for this question. All right, well, I hope that was helpful. I'm going to come back with a couple more questions as soon as I can. Have a good one.